Hold on.
There we go. I didn't have the mic up. Hi, everybody. Welcome back to Chem 121. And Maya is here. Maya, say hi. Maya? Okay, hopefully you heard that. Welcome back to Chem 121. It's week 4, which means that we're already a third of the way through the class. Like, holy crap. When did that happen? Well, it happened last week, and the week before that, and the week before that, too. I don't know where I was going with that. I just thought I would let you know. What's due this week? So quiz number 2 is due today, actually. Make sure you get that in by tonight. It will close tomorrow, so you have 24 hours if you absolutely need it. That assignment closes on Wednesday. So the quiz for this chapter is actually due on Thursday, and it will close Friday. We only have like 3 more slides to talk about for this chapter anyway, and I'm not super concerned on your ability to refer to the notes for these if you really needed to. So I put the quiz up for this week, as opposed to having it pop up next week, because we have a few more chapters to get done before the exam, and there will be quizzes on those, and I want to make sure that you don't have all of them stacked on top of each other. So, all right. Lab worksheet number 2 also will be assigned this week. Quiz number 2 is all the stuff from chapter 2. So, conversions, density, maybe a temperature problem, stuff like that. But yeah, it's everything from chapter 2. What is my cat doing? What are you two doing? Sorry, I'm staring my cats down because they're staring me down. But yeah, all the chapter 2 stuff is quiz number 2. The quizzes are by chapter, for what it's worth, so you'll always know what to study. Oh my goodness, I keep hearing them, like, fighting. I might have to go break up a cat fight in a second here if they start yelling. Okay. So, let me get p-table out here. P-table. We'll paste this in the chat here again for you. Again, you should have this handy. So let's put that on the screen here. I want p-table. That's you. And boop. All right. So here's our periodic table. You'll notice that we have a bunch of numbers on the side here that list each row 1 through 7. And then a bunch of numbers on the top here that go 1 through 18 going up and down. These numbers along the top, categorizing our columns, are what are known as groups. So, group 1, group 2, group 3, group 18, so on and so forth. So, groups are columns, and columns run up and down. So, I'm going to highlight everything you need to know there, because I know from personal experience that I get column and row mixed up all the time. So columns go up and down. So those are called groups. And they go from, here, let's actually write this down. So groups go from 1 to 18. However, there's another numbering system out there that uses the letters A and B. And I used to think that this is the best numbering system for a very specific reason. But I've since come to appreciate that all it does is really confuse people. Like, why is it B? Why is it A? So, the A and B numbering system comes from Mendeleev and his periodic table, where he had things occupy the same boxes. And so he had one set of elements called A, and the other set was B. Nowadays, we've just sort of numbered everything all the way across 1 through 18. So, both of these numbering systems are useful to us. But for the purposes of this class, whenever I see something that looks like this, I'm going to renumber it so it's in this scale. And so I'm going to just call things 1 through 18. I noticed that I dropped frames there. Hopefully I didn't stutter out for a second. We're going to use the 1 through 18 scale. And so that's going to match up with this periodic table here. So if I ask you, name an element in group 11, you would say copper, silver, gold, or roentgenium. I don't know who that was, but personally, I would pick gold. That's the most expensive. I'm more of a platinum guy myself, but that's group 10. All right, so those are our groups. The next property of the periodic table we want is going across left to right. And so rows going left to right are called periods. And so those are right here, these numbers right here. 1, 2, 3, 4, 5, 6, 7. These are pretty straightforward. If I said name something in period 4, you just say, oh, okay, I'm going to pick something in this row. And you're all set. But if I said name something in period 6, you could pick anything in this row, but you could also pick anything between 57 and 71. So these are actually also in period 6. And it's numbered on this table very conveniently. Most periodic tables actually don't number these two down here. But these two rows are shown here because if I hit this button, this is what the periodic table actually looks like. It's just really long and cumbersome, and now there's a scroll bar, and I had to do this to it, right? That's obnoxious. Nobody is happy with this. So we'll turn that off, and we'll save some space. So that's really why those two rows are down there. It's just, if we put them where they belong, the periodic table would be extremely long. So whenever you see a periodic table and you're like, why are the two rows down at the bottom? They actually aren't. It's a shortcut. We're just putting them down here because we can use this space. Okay, so you should be able to name, if I gave you an element, so like say this one, I just clicked randomly, you should be able to tell me what group it's in, that'd be group 18, and what period it's in, that would be period 4. All right, no problem. All right. On the screen here are some names of things that I feel are useful enough that you should commit them to memory. And so that's going to be the names of these groups up here. So I'm just going to highlight the important ones. We're not going to highlight Chalcogens because nobody cares, but that's okay. All right. Group 1. Oh, right, I can't write on this if I'm zoomed in because Microsoft is dumb. And group 2. And you'll see this is the A and B numbering scheme. You can see, like, what the hell's going on here? Right? So that's why we're not going to use that. And let's just fill these in because these are the important groups. There we go. Now I can zoom in. Group 1 is what's known as the alkali metals. Ooh, excuse me. And group number 2 is known as the alkaline earth metals. What does it mean to be alkaline? You've probably heard of something called an alkaline battery. And what that means is that it contains an alkali or alkali earth metal. Actually, now that I think about it, I'm not sure if that's true. But the definition of alkaline means basic. So when we get to chapter 10, we're going to learn about pH and how you can have something that's acidic versus alkaline. And I'm thinking about it now, and I'm like, wait a second, I don't know of anything. None of these elements would be in a battery. The battery would explode. Or produce hydrogen gas. We don't want that. I think it's just in like a sodium hydroxide paste or something. I have to look that up. I don't remember battery chemistry, but that's okay. So anything with the word alkali or alkaline in it is basic, because that's what that means. So, and I'm not sure, actually, if batteries contain these elements, but putting any of these elements into water produces a base. What ends up happening is it reacts with water. It removes an H plus ion, 2 of them actually, gets reduced to hydrogen, and then the hydroxide that's left over in the solution forms a basic, the alkaline component. So because all these elements do that, they gave them these names. They're common enough we should know those names. So alkaline metals are in group 1, alkaline earth metals are in group 2. Over here on the far right, these two groups, the noble gases are group 18, and the halogens are group 17. Halogens are important because they're very, very reactive, and they have very, very useful purposes for various applications. For example, chlorine Being a very toxic gas, you might think, oh, there's nothing I can use with chlorine. But chloride, which is the ionic form of chlorine, is absolutely everywhere. Chloride is the counterpart of sodium in table salt. It's also used as an ion buffer in intracellular fluid. Other things that chlorine is used for include halogenation reactions. It can be used to clean stuff, so like we throw it in the pool. And yeah, that's basically... The chlorine is the big one for halogens. Iodine is important for thyroid health. Fluorine is important for your teeth, but fluorine otherwise is quite toxic. And then bromine, I know it's in sea salt, but I'm not really sure if bromine has biological, not considerations, I'm thinking about, uses or applications. Like, I'm not sure if it's healthy to be eating, like, lots of bromine. Probably not, right? So that group, halogens, group 17, and then the noble gases, group 18, are worth memorizing the names of. The noble gases are very special. We'll talk about those in chapter 4 a lot. Noble gases don't react. They are too hoity-toity for the riff-raff of the rest of the periodic table. What that means is that if you put neon in a container with any other element, it does nothing. Neon will just hang out. Argon will just hang out. Krypton will just hang out. Xenon will just hang out. Radon is actually radioactive, but besides the fact that it decomposes, radon would just hang out too. It doesn't do chemistry. So, like all nobility, the noble gases sit on their asses and do nothing. All right. So those 4 groups I feel like are worth knowing, and then I'm going to add on some extra ones. So the Chalcogens, nobody cares about the Chalcogens. Like, that's not a name that I have seen anywhere outside of literature. And by literature, I mean people who write scientific articles for a living. Not worth committing to memory. Things that are worth committing to memory, though, are the following. So this range right here from groups 3 over to 12... So 3 to 12. These are what are known as the transition metals. And what the transition metals do are they are the transition from the left groups to the right groups. That is actually the name of the metal. That's why they're named that. Which is kind of stupid, but when you consider that the groups 1 and 2 and then 13 through 18 are called the main group by chemists, then the transition from one part of the main group to the other makes sense. But we don't really care about the main group. I'm not going to use that term in this class. So, transition metals, however, is a common enough term that you will hear people mention it. So, like, iron is a transition metal. Chromium is a transition metal, and so on and so forth. Down here, these are called the lanthanides. Or lanthanoids, I guess I should say, and actinoids. And the reason for that is because these elements, lanthanum and actinium, are the start of the shortcut. And so they're written there. Now you might notice that if I go back over here to p-table, that lanthanum and actinium are actually down here at the bottom to start these rows. Here they are. And that's fine. Some periodic tables will put them in the space, and then just there will be a 57, and it'll go straight to 72, and it'll be up to you to infer that, oh, I should probably go down here. Does not really matter where they're placed. We're going in number order anyway. Those are the main names that I personally think are important. The highlighted ones, the ones they added in red. There is a name for the group 5, not 5, but 15 elements. The Nictogens, and I had literally never heard of that until I had started teaching from the textbook that had that name in it, which was like 3 years ago. So I don't think people need to know that they are Nictogens, so whatever for group 15. And then Chalcogens again, same thing. All right. So what I want you to do here is, based on all of those names that I gave you on the previous slide, I want you to assign each of the following elements, give it its name, write down what period and group it's in, and then label it as alkali metal, alkali earth metal, halogen, noble gas. But we're also going to add in either transition metal, lanthanide, actinide, or none of the above. All right. I'm going to number these so that you have you can type them in the chat if you'd like. There you go. Go ahead and do all those things. We'll check in about 4 minutes. One more minute, we'll go over the answers. All right, so let's put this on the screen here, but we're going to just slide it over here. Got to cover you guys up for a second. Sorry. Sorry, chat. All right, so let's find these elements. So the first one is AT. That's over here. Boop. So Astatine is in group 17. It's in period 6. And then I want to give it a label, and that label I would give it would be halogens. So Astatine is a halogen. Even though it's radioactive, it's still in group 7, so we'd still call it a halogen. How about potassium? Potassium's over here. Boop. Potassium is in group 1, period 4, and is an alkali metal. You can see the name of that right there. There it is. What about gold? Here's gold right here. Boop. Gold is in group 11, period 6, and is a transition metal. And then we've got rhodium, which is also a transition metal, but it's in group 9, period 5. And then finally, tellurium is group 16, period 5, and you could either write chalcogen or none of the above. Tellurium is one of the stinkiest elements when paired with hydrogen. In fact, if you are ever exposed to H2TE, hydrogen telluride, you probably will never smell correctly again. Everything will just smell like death. The stinky substance that we're familiar with is H2S, and as you go down the periodic table and pair these with H2, they get worse and worse and worse. So, just a fun fact. All right, there's the homework practice for this section. We have one more thing to do for Chapter 3, and we're going to do that in just a second. But I am going to go back a slide and indicate, hey, what's this thing that I'm drawing over with the mouse when I have a pen? I don't know why I'm doing that. So that zigzag, unfortunately, does not show up on this periodic table. It instead shows up as a series of colors. And so you could see that between these two elements would be a sort of zigzag that goes down like this. Almost. We'll talk about what that zigzag means in just a second on the next section here. All right, this is the last section of Chapter 3 that we're going to care about. There is a property that the periodic table reveals called metallicity, or how metallic something is. You might think that that's a binary thing. Something is a metal or it's not. And you're sort of on the right track, but there are various properties that all metals have in common, and if we take away all of them, you get a nonmetal. But what about the things that have some of those properties? And those are in the area that I showed on the periodic table. So let's discuss what those properties are. Uh-oh. I clicked on the wrong thing. There we go. There we go. We're going to define a metal as a substance that has all of these properties. So it has to have all of them. It cannot get away with just one or two. And so the first property is that it is conductive of electricity and heat. Metals are very good at conducting both of these things because electricity is the flow of charged particles. Electrons are very mobile in metals based on how their bonding happens. And they're easily able to conduct heat because all of the metal atoms are very, very, very close proximity to one another. So they just vibrate and bonk into each other and move heat through them, move heat through the metal efficiently. Another property that's important for metals to have, to be metals, that is that they have to be both malleable, which means that you can hammer them into a sheet, or if you hammer them, they don't shatter or break, they just deform. And also ductile. Ductile means that if you pull it in one dimension, you can get a wire of increasing thinness. So if I want to make, like, say, copper wire, what you do is you take a chunk of copper and you pull it, and then you pull it, and then you pull it, and then you pull it. And can you guess what you do after that? You stop unless it isn't thin enough, in which case you pull it, and then you pull it, and we'll stop that. But this is how you make wire. You just pull on metals. They won't break. The metals want to stay one contiguous piece, and when you apply a force to them, they change their shape. The last important property of metals is that they're shiny. So luster, like Bender here. Apparently this show is coming back. Futurama is coming back. So my Bite My Shiny Metal Ass reference will be topical again. Metals are shiny due to the fact that the electrons over their surface can absorb light and then reflect light. And in doing so, you get this nice little sheen. And depending on how you paint out your metal, you can actually create a mirror and reflect all the light. So all metals have this property. They are all shiny. They all have luster. They all reflect light very easily. And metals have all of those properties, all 5 of them. Now, if you are a non-metal, you have none of these properties. For instance, iodine does not conduct electricity, nor does it conduct heat well. You cannot hammer it into a sheet or a wire, and it is not shiny. Instead, it is purple. It is the most purple. But that's what it has going for it. It doesn't have any of the things that metals have. It just has purple. So those are nonmetals. All nonmetals are like that. But there is an in-between region where we have stuff that is sorta, kinda has some of these properties. And so silicon, for example, I mean, it looks a little shiny. This is pure silicon. It looks a little shiny, right? Now, the thing about silicon is that it does not conduct heat super effectively. And that's useful for our purposes because when we make things out of silicon, like, say, a computer circuit or a chip or a circuit board, stuff like that, using silicon, we don't want it to heat up to the point where it melts, right? So we are passing a lot of electricity through our silicon chips for our computer, for our smartphone, for our television, whatever. All circuit boards are made with some amount of silicon in them, right? And so, because silicon resists heat transfer, it does not transfer heat as effectively as, say, copper does or aluminum. It doesn't heat up as much. And that's good because we don't want our computer to melt. So elements that are metalloids have some of these properties, but not all of those properties. So real quick, we'll highlight the homework practice here and then show you which elements are metalloids. And those elements are the elements that touch that zigzag that I had showed you earlier. So I'm going to draw it in dark blue here because black doesn't show up super well. We'll do that. Okay. So if you touch the staircase, you are what is considered a metalloid with 1 or 2 exceptions. And the most important exception is aluminum. And then these down here are radioactive, but polonium and astatine are also considered. Polonium is considered a metal, and astatine is considered I don't know what astatine is considered. It's radioactive. Nobody gives a shit. P-table has it listed as a metalloid, but whatever. So what you need to know is that this staircase that I drew, starting up here at boron's corner, and they're just going down, right, down, right, down, right, down, right. Everything that touches that except for aluminum and polonium is a metalloid. And so the metalloids are the substances that are sort of between metal and non-metal, and have various applications that we use them for. All right. That's it. That's chapter 3. We're going to skip all these remaining slides, so we're going to just do this. Woo! We're just going straight to the end here. Hooray! And if I click this, it should play a sound, but it didn't play the sound. Maybe if I do this. No, nothing will happen. Okay, great. I will just exit the slideshow. Give me a second and I will get chapter 4 on your screen here. Oh, I don't want to do that. I want to start at the beginning. Okay. All right. Starting with chapter 4. Oops, hold on. My screen is freaking out here. There we go. Okay. Starting in chapter 4, we're going to start using a list of ions. Oh, wait a second. Hold on. What are the two elements that aren't metalloids? Did I write those? So polonium and astatine. I wrote that, right? Let me know if I didn't. We'll just put this back on the screen. So I believe we were referring to these two down here, which P-table lists as a metalloid. They're radioactive, so it's not super important to know that. Polonium is just like super radioactive. Like this is, I want to say that this was used to like kill somebody as a poison of some sort in like Soviet Russia, like back when it was the USSR. So like before most people were born, probably before I was born, but I don't actually know. All right. So chapter 4 is going to require us to use a specific set of ions called the polyatomic ions. And the list of these is on my next slide here. Your textbook has a list of these, but depending on the edition of your textbook, you will have more or fewer ions. And so what I want you to do is, so write down somewhere in your notes, second slide of chapter 4, you want to have these ions available to you either for when you need it or to commit to memory, because you are going to basically use these all the time in biology. Like when we get to biology 211 and they say phosphate buffer, you're going to need to know what phosphate is, and that's this right here. Like, that's going to be super crucial. Or if I say carbonate, you should know what carbonate is, or hydroxide. These are all going to be very common things that we use in biology and also in this class. So they're worth committing to memory. However, you don't have to because this is an online class, right? So have the reference handy, or commit to it by using flashcards or just doing enough problems and you'll eventually memorize these. Now, you do need to know the name, but you also need to know the formula. So the formula is both the elements and also the charge that is written. Notice that all of them are negative except for ammonium, which is the only positive one there. All right. Chapter 4 is about ionic compounds. And what we're going to do is we are going to discuss how we form bonds between elements. And then we're going to start drawing pictures of that. So our goal in chapter 4 is to take the idea that elements will react with each other by interacting with their electrons, and then make pictures out of it so that we can understand patterns in drawing structures. And so that's what we're going to do in this chapter. So the first thing we want to do is talk about what a bond is. A bond is any interaction that holds two atoms together to form a molecule. Now, I should clarify that that is at least two atoms. So you could have more than two atoms bonded together. In fact, you could have one atom could be bonded to up to 4 atoms, and each of those could be bonded to up to 4 atoms. Oh, excuse me. And each of those could be bonded to, and so on and so forth. So you can have all sorts of crazy bonding going on. So a chemical bond is an attractive force. Oops. Sorry, I have my tablet tilted the wrong way. Now it's tilted too far this way. I gotta find the correct amount of tilt. There we go. There we go. So an attractive force holding the atoms together into the molecule. Now, there's going to be 2 types of bonding that we're going to care about in this class. Oops, I didn't mean to skip past that. So the first one that we're going to talk about is Chapter 4, Ionic bonding. And the covalent bonding we're going to talk about in Chapter 5. Both of these types of bonding lead to very different types of compounds. For the ionic bonding chapter, we're going to look at ionic bonds, so things like table salt, which have extremely high melting and boiling points. They're soluble in water, and other things that we'll mention. In Chapter 5, when we talk about covalent compounds tend to be insoluble in water to some degree. Some are soluble, but a lot of them aren't. They have very low melting and boiling points. They don't conduct electricity. I'm trying to think of other things that covalent compounds don't do. And some are even gases at room temperature, like oxygen that you're breathing right now. If you aren't breathing, remember to breathe. It'll be okay. Don't panic. All right, on the screen I have some ionic compounds. A feature of ionic compounds is that they crystallize into cubes. And so down here, you can see my sodium chloride crystal. This salt crystal is very, very cubical. In my fool's gold, you can even see the cubes in the surface. I'm going to try and draw some of these in here. But you can see how my solid has tried to crystallize in a manner so that there are very flat faces. And the reason for this is because ionic compounds form by the attraction of ions. And the most attractive locations in an ionic compound are those where there are the most number of neighbors. So being surrounded in the center, like I'm pointing in this cube, like inside its guts, would be the most ideal. But if you were on the surface, like say this one right here, you're surrounded by 5 neighbors, the one directly inside from you, and then the 4 around you. That's a lot of neighbors, and that is the best place you can be to be attracted to as many other ions as possible. The worst place to go would be to put yourself on top of a new layer, because then you would only be touching the neighbor that is directly inside from you. So making it a regular surface where ions just sort of go wherever they want to is not preferred because they want to adhere to each other as much as possible. And so they will arrange in such a way that this is possible. If there is an edge that they will fill in, they will do that. But if there is a gap where they can fill in like the middle of a plane, that is the best possible outcome. And then if a new layer forms on top of it, it will quickly propagate in all directions other than outward, because that will maximize the amount of bonding. So what ends up happening is that we just end up forming these cubic structures. All right. On the screen are some various properties of ionic compounds that I just mentioned. So those include things like they have very high melting point. I didn't mention this, but they also do this. They conduct electricity when dissolved or when molten. So if you take table salt and you put it in water, it will dissolve. You can then hook up a series of wires connected to an electrode, and it will serve as a conductor. And then we just mentioned that they are crystalline and they form cubic structures. And virtually all minerals that you mine up are ionic compounds. Very few exceptions to that rule. Those would be elemental things like gold. Gold you mine up, it's just gold. Platinum you mine up, it's just platinum. I think silver might actually be an ore. I don't know if it's an ore or if it is a mineral. It might be an ore. Oops. All right. Now, if I go back over here to this picture real quick. So this is a zoomed in picture of a crystal lattice. And you can see that I have various ions here. I have sodium, which are these little purple spheres here, the smaller ones. And I have chloride, which are the bigger green ones. And they alternate in a very regular pattern. Plus, minus, plus, minus, plus, minus, plus, minus. That pattern will persist throughout the entire ionic compound. If I take the simplest form of that pattern and I can copy and paste it, that's the chemical formula of the ionic compound. So that's known as a formula unit. So we could write that down here. If I can select the right writing utensil here. And so the formula unit is both the formula of the ionic compound, it is the simplest ratio of the elements, and also what you can copy and paste. Now, in reality, we would be copying and pasting a three-dimensional cube sort of thing. But if I were to just circle a pair of these, and you go copy and then paste, 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 you could create the whole ionic compound. I am oversimplifying that for this class because we don't talk about the structure of solids. You do not need to see the unit cell. You can look that up if you want, if you're curious, and you'll see why I didn't do that, because it splits atoms into pieces. But the formula unit is going to be the ionic compound's quote-unquote molecule. Ionic compounds are not molecules. They are formula units that form a lattice. All right. So what does this look like at an individual ion level? It looks like this. I'm going to have some cation. Cations are positively charged. I'm going to have some anion. Anions are negatively charged. And I'm going to stick them next to each other. In doing so, they are attracted. Opposite charges attract to each other. We talked about that in Chapter 3. Same charges repel, but fortunately, I can arrange my ions such that I only ever have opposites next to each other. Because I can just alternate, right? Plus, minus, plus, minus, plus, minus. All right. This is a little bit of a heads up from Chapter 5. We're going to talk about Chapter 5 in great detail, but for now, what I want to share is just that what covalent compounds are. They're different from ionic compounds. Covalent compounds have low melting points. I can't select the thing. There we go. So, low melting points and do not conduct electricity. Now, some solid covalent compounds look like they are crystals, but in reality, they are just a bunch of molecules stuck together to form random shapes. So these sugar cubes here, you can see that there are tiny little sugar crystals, but if you zoom in on those, they are not a regular shape at all. And the reason for that is because sugar is a molecule. Here's its formula, C6H12O6. And molecules in solution are independent of each other. So you can see here that this water molecule is totally independent from this water molecule, which is independent from this water molecule, which is independent from this water molecule, and so on and so forth. They are all individual, and they can rotate randomly and move around and bounce off of the container walls, bounce off of each other, but they don't get stuck to each other. Covalent compounds form legitimate, actual molecules. All right. I think we're due for a break because that's we're going to talk about this all in Chapter 5 here. So before we go into the next section, we'll take our break. Let's see here. So they look like cubes, but when we get close, they actually aren't cubes. So if you try and like powder up sugar, it's very easy to make powdered sugar because you don't end up with cubic things. Making powdered salt is a lot harder. Like you can grind up salt into popcorn salt, but salt will try to keep its cubic structure if it can. Sugar has no incentive to, because the bonding in covalent compounds doesn't allow molecules to stick to each other through what we would consider bonds. We're going to talk about those interactions in Chapter 7. And if you remember this question, like, hey, why do sugar form a cube? We can talk about that in Chapter 7, because it'll make more sense then. And then is the exam Chapters 1 through 5? Yes. So it's the first 5 chapters. All right, so let's go over here, get the timer going. I realize Chapter 7 is a very long ways away, so probably won't remember that. But when we talk about intermolecular forces, and I say this is how molecules stick to each other, it'll make sense. All right, I'm going to start the timer. Enjoy a 10-minute break, and we'll see you when we return. Sorry, I'm trying to find the music that I want here. Unfortunately, I don't know how to alphabetize. There we go. Hi everybody, welcome back. Wow, that's 2 times in a row I've landed exactly on 10. Let's wind this down here. So I sit here and I like stop the timer when it's 10 minutes because otherwise it would just run forever. Alright, so I have I went and got more water. My water comes in cans because I'm a middle-aged adult and all I drink is seltzer water now, I guess. I don't know. Alright. We're going to do the pictorial representation of bonding now, and so it is known as the Lewis symbol. So the Lewis symbol is going to represent a single atom, and then what we're going to do is we're going to put multiple atoms together and then do things with the dots that we draw around them to indicate bonding. And so that's going to be our objective for the rest of today, is to figure out how to represent bonding with these Lewis symbols and structures. So let's do that. Well, we could do that if the slide would advance. There we go. All right. On the screen here, you have pictures of various elements. So underneath, I've written the atomic number, Z equals whatever. And I've also drawn enough electrons so that the neutral atom would be represented with the correct number of electrons and protons. Now, I have highlighted certain electrons. Namely, I have highlighted the electrons that are on the outside of the atom. Because if I have 2 atoms, let me select the pen tool. I already have selected. So if I have 2 atoms, like this, and I bonk one into the other one so that they impact, what would actually end up encountering the other atom would be whatever layer of electrons are on the outside and whatever layer of electrons are on the outside of that atom. All of the stuff in the middle doesn't do anything. It doesn't actually get to see what's going on. And as a result of that, we only really care about the electrons on the surface. These are called the valence shell electrons. The valence shell is the outermost shell of electrons. Now, don't worry too much about... Oops. Well, I just drew poorly there. Don't worry too much about why we have these arranged in rings how we do, because that's a little beyond the scope of this class. But what we can divulge is that electrons repel each other, and there's only so much space around an atom. So as I start stacking electrons around my atom, I can't jam extra ones in there because they would repel each other. And what ends up happening is, oh, I just have to make a new layer. Now, when I make a new layer, it becomes the outside layer, or the valence shell. And the number of electrons that will be on the outside is always between 1 and 8. We're going to keep that in mind later. All of the other electrons that I didn't highlight here end up being buried under the new layers as they are formed. And so those inner electrons, which are also called core electrons, they don't bond. They don't participate in bonding. They don't do anything. They just hang out. All right. Now, if you go to the periodic table and you look at the group number will tell you how many valence electrons there are for a given element if you're looking at this A notation. Now, unfortunately, we said that the A notation is Garbo now. So what we're going to do is we're going to do this. We're going to get rid of these, and then I'm just going to number the groups. Like this. And then what we're going to do is we're going to underline all the ones digits. And I'm only going to do this for the main group elements, and we'll talk about why in a second. So whatever the ones digit is going to be the number of valence electrons for any element that is in that group. So if I say, how many valence electrons does hydrogen have? You would say, oh, 1. How about sodium? Oh, also has 1. What about carbon? Well, the ones digit is 4, so it has 4 valence electrons. So you can now count valence electrons based on what group things are in. Now, why are we going to skip these in the middle? And the reason for that is this is literally my major. So when I went to college, I studied the transition metals. This is literally the thing that I have a master's in, and it's not a first quarter topic. So it is much more complicated because transition metals actually do all sorts of really crazy, interesting things, but they don't model well to the rules that we're going to teach you for bonding, so we're going to ignore them. So ignore transition metals. We're going to just focus on groups 1 and 2 and 13 through 18. That's going to be the 8 groups that we care about for counting valence electrons and also figuring out what bonds will form between those atoms and how we arrange the electrons. There are other types of bonding beyond the scope of this course. And the rules that I am telling you, like these only do this and these only do this, work specifically for this class, which encompasses like most compounds that you will encounter, but not all, certainly. And so there is other weirder, more esoteric shit out there. Okay. So let's start drawing pictures. So what we're going to do is we're going to take our idea of how many valence electrons does something have, and we're going to apply it to a picture. And so that picture is going to be called the Lewis symbol. And the Lewis symbol is named after, I want to say his name was George. I don't know. Every quarter I tell myself I should just look this up. Gilbert was his name. Gilbert N. Lewis. Every textbook refers to him as just Lewis because the Lewis symbol is the most important thing in chemistry in terms of communicating a picture with an intent to it. Beyond all other topics in this class, this one I think is probably the most chemistry in terms of if you see this, you will immediately go, oh yeah, that's chemistry. And you've probably seen it before. You've seen stuff that looks like this, right? Things like this. These are all Lewis structures. We're going to start with really simple ones, and we'll talk about this organic nomenclature, or not nomenclature, but how it's drawn in organic chemistry in chapter, I want to say it's 8. I'll briefly introduce it to you so that if you do take 131, you'll have seen it before. So here's how you draw a Lewis structure. Symbol, I guess I should say, for the individual atoms. To draw the Lewis symbol, you have to do 2 steps. The first step is to write out the symbol of the element. So if it's sodium, you'd write Na. If it's oxygen, you write O. If it's hydrogen, you write H, etc. And then you want to draw dots around the element, and you get 1 dot per valence electron. And we just learned how to count how many valence electrons there are by looking at the ones digit in the group number. So let's do that. We're going to do the Lewis symbol for sodium. So 1, draw the symbol. There you go. 2, draw a dot for each electron. So if I go back over here to the periodic table, which is asleep, hold on. There we go. And I click on sodium. We see that sodium is in group 1. So it must have 1 valence electron. So I'm going to put 1 dot around sodium. There you go. It's done. This is the easiest thing you'll do in this class, isn't it? All right, let's do another one. I want you to draw the Lewis symbol for oxygen. But there is a caveat. Remember that electrons repel, so first step, draw oxygen symbol. Okay, yeah, duh, O. Now when you put the valence electrons around it, note that there's really only limited places to put it. So we're going to limit those places to the 4 sides. And what you should do is you should put 1 electron in each spot and then start pairing them. And the reason for that is electrons repel, right? So electrons will only pair if they have to. When you run out of sides, you have to. So draw the dots around your oxygen in a way that you think would be the Lewis symbol for oxygen. And we'll check out your answer in about 1 minute. All right, hopefully you have drawn something. So here's what I drew for my solution. So if we count the number of valence electrons, first we would go to P table. We find oxygen, so there it is. Oxygen is in group 16. The 1's digit is a 6. That means oxygen has 6 valence electrons. We would draw 6 dots. We're going to draw 1 dot for each valence electron. And we're going to put 1 on each of the 4 sides. Before we start pairing them. And there you go. Now, does it matter which 2 sides you have them paired on versus unpaired? And the answer is no. So, if I drew this, so 1, 2, 3, 4, 5, say 6, that's fine because I can just rotate it around, right? However, if I did this is also okay. All that matters is that for 6, you have 2 unpaired and then 2 pairs. What would not be okay, so these are all both okay. What would not be okay would be to draw this. So this one is not okay. I'm not sure what you mean by what's up with the yellow. I don't have any yellow on my screen at the moment. You might be behind the video, I'm not sure. So, what's the problem with this one right here? Well, the problem is that I have this region down here. Now I'm going to draw in yellow. Actually, you know what I'll do? I'll just draw a different color. So, this one's wrong because I have an empty space here, and because electrons repel. So, because these 2 electrons are next to each other, and so are these, and so are these, and there's all this space down here, one of these is going to move to fill in that space. So the reason that it's wrong is because this is just how things work when they repel. Is they want to maximize the available space between them, so they wouldn't just leave an entire side empty. Oh, the yellow around the circle was just the 4 sides of my atom. All atoms we're going to consider to have 4 sides around them. How did I come up with 6? So this is oxygen. Oxygen, remember, we're only drawing dots for valence electrons. So when I count valence electrons, oxygen is in group 16 and has 6 valence electrons. It has 8 electrons total, but on the outside, where there are valence, only 6 of them are on the outside. So that's where the 6 comes from. The first 2 are for hydrogen and helium, so that would be row 1. And then we make a new layer, which would be these, leading up to it. All right. So again, when we're drawing this, all that matters is that you have the correct number of unpaired and the correct number of paired. And there's only one way you can do that. And the way that you want to do this is you just want to pick a side and start dotting around. Dot, 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 until you're done. And you'll always get the right answer. One per side. So, yeah, we can do another one. I mean, I'm going to give you a bunch of these, but we'll just do... Let's do phosphorus. Phosphorus isn't actually on here. So that's a good example to do. So let's find phosphorus on the periodic table. So phosphorus is right here. It's in group 15, so it would have 5 valence electrons, because that's the 1s digit. So now I got to draw 5 dots for phosphorus. And so we would do 1, 2, 3, 4, 5. So that'd be phosphorus. So your job here, count all the valence electrons for each atom. So go to the periodic table, go to P table. The link should be up here in the chat. Let me find it. Yeah, it's right here if you scroll up to the top. Count the number of valence electrons that each element has by looking at what group it's in and taking the 1s digit. So carbon, for instance, is group 14. How many valence electrons is that? And then draw the appropriate number of dots. Now, obviously, you cannot put this in the chat. There's no way that you can draw these in the chat effectively. So I will just give you about probably 3 or 4 minutes to do this, and then we'll go over the answers. And if you're finished, you can just type done or something like that. All right, see you in a bit. All right, 1 more minute. We'll go over the answers. All right, so what I'm going to do is I'm going to click here, and I'm going to make this real tiny. And we'll put this up here. So, and then what I can do is I can just click on the element that I want. So for this first one, I got carbon. I just realized that doesn't help me, does it? Can I do, there we go. Because we need the group number. Okay, so I'm just gonna have to turn this on and off repeatedly. So, okay, so carbon is in group 14, and it has 4 valence electrons. So to draw carbon's Lewis structure, we would draw this. So 1, draw the symbol. 2, draw a dot, 1 dot per valence electron. It should look like that. All right, lithium over there in group 1 has 1 valence electron. So I would draw it like this. So Li, and I put a dot next to it. Now be careful, this is the only element that this happens for. That dot over the I in lithium does not count as its valence electron. So just be mindful of that. I have seen people actually draw that where they said, well, I did draw a dot. It's the I on lithium. Like, wait, no, that's not how letters work. So that's the only letter I think that comes up. Oh, well, I guess silicon could do it too. Bismuth, but we don't really use bismuth that much. All right. Sulfur is in group 16. So it has 6 valence electrons. And so we do sulfur, 1, 2, 3, 4, 5, 6. Oops. Chlorine is in group 17. So it has 7 valence electrons. So we'll draw 7 dots for chlorine. So it's chlorine, 1, 2, 3, 4, 5, 6, 7. And again, it doesn't matter which side your unpaired is on, as long as there's only one unpaired. For chlorine, there's really only, that's the only solution that you can draw anyway. Aluminum, we'll go like this. There's aluminum. Aluminum's in group 13. That means it has 3 valence electrons. Al. 1, 2, 3. And then xenon over here. There's xenon. It's in group 18 with 8 valence electrons. So we would draw all 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. There you go. Now, it turns out 8 is the maximum, and 8 is actually going to be kind of special. So we're going to talk about 8 in a little bit. There's the homework practice for this section, though. Disney's Atlantis. That's not where I would have gone with this. I mean, I guess it could be some sort of like code or something, but... All right, so now what we're going to do is, you probably remember me talking about noble gases, how they do nothing. Well, it turns out getting 8 electrons is permission to do nothing. Because any ion or atom with 8 valence electrons is very stable. This just happens to be an arrangement of electrons around a nucleus that results in a particularly stable ion or element, if you're a noble gas. And so what atoms are going to try and do is they are going to look at their number of valence electrons and go, hey, I want to have 8 valence electrons. And so its goal will be, if you don't have 8 electrons, gain or lose electrons so that you have 8. And when you get to 8, you stop reacting. There are no more electrons that need to be changed. So this is called the Octet Rule. The Octet Rule is just basically, I want 8 electrons. Sorry, I'm scratching my ear here, so I had to move the headset. I want 8 electrons. I will do anything to get 8 electrons. Now, how does this work? Let's look at an example here. So here's oxygen. Oxygen wants 8 electrons, but it doesn't have them. It has 6. So what oxygen is going to do is it's going to say, well, I only need to take 2. Wow, that was a pen stroke, you guys. All right. So if I steal the electrons here, I can get to 8. So I'm going to steal 2 from something. And then I do this to it. Boop. There you go. Now you'll notice that in doing that, I had regular old O before, but now I have O2- because I have an ion. The number of electrons and the number of protons in this atom are no longer the same. I have 2 extra electrons than I started with. So I have to indicate that. My charge has increased by -2. And so I indicate that on both the formula and also the structure by writing it. Noble gases are extremely stable, yeah. Helium, neon, argon, I'm not sure if there are any compounds that are known with them. They don't react with anything. They just hang out. There are some very, very, very rare compounds that can form with like xenon and krypton. But it's extremely unlikely. So by adding 2 electrons to oxygen, we have made it O2- or oxide. We'll talk about the names later. But we have added 2 electrons, so we've changed its charge from 0 to -2. All right, so adding electrons is pretty trivial. We just have to get to 8, right? Now, what if you are an element on the left side of the periodic table? Those elements have very few electrons, and adding a bunch of electrons is difficult. So what these atoms actually opt to do is the following. I'm going to show you the following, and then we're going to look at what actually happened here. So here's my sodium. It's going to get rid of its electron. And you might think, well, wait a second, that's not 8, that's 0, right? But let's go back over here. Remember on the first slide that I showed you where I had this? So we're going to look at potassium here as an example. And what I'm going to do is I'm going to... Is this a color that I can draw? No, it's like erase or something. Okay. Sorry. I'm trying to find... Oh, this will work. Okay. So what I'm going to do now is I'm going to say, I'm going to remove this electron. Let's see how many valence electrons I have now. Well, if I remove this, I also remove this entire layer. How many valence electrons are there now? Well, let's find out. 1, 2, 3, 4, 5, 6, 7, 8. Look at that. There's an octet hiding beneath my layer. Remember that because we're just doing layers upon layers upon layers, right? And the highest number of valence electrons I can get to is 8. If I put more electrons on top of that, I just start over, right? So by deleting all of the electrons in the valence shell, the previous shell becomes the valence shell. And therefore, we hit an octet. So this will happen for all of the elements on the left side of the periodic table, with a few exceptions. Those exceptions being things that are like up here, so like lithium, beryllium. These are too small to hit an octet. They follow a different rule. But for any other element, so anything past like 5, it all follows the octet rule. So now we go back here to our sodium. We can say, okay, well, if I get rid of this electron, now the previous layer of electrons that, say, neon had, because neon is the element before sodium, that will be my octet. So the takeaway here is that if an atom has 0 valence electrons, treat it like an octet. Because in reality, there is an octet. It is just buried under the layer that you just removed. All right. And this is literally everything I just said, so we're just going to move on to the next slide. So now that you have seen this, what I want you to do is I want you to look at these ions that I have created. And so what I want you to first do is we'll do the potassium one together. So first draw the element and draw out all its valence electrons. So potassium's in group 1. It has 1 valence electron. And then what I want you to do is I want you to apply the charge to it. So if I want to make it positively charged, I have to remove the electron. And then what I want you to say is this an octet? Does it resemble a noble gas? Yes or no? And so if your answer is, well, I landed on 0 or 8, then you would say yes. For this one, however, you'll notice that for calcium, here's what calcium starts as. It has 2 valence electrons being in group 2. I'm going to get rid of 4 electrons, so I have to get rid of these 2. But then I would have my octet, but then I have to get rid of 2 more. So this cannot be an octet. Calcium plus 4 is not resemble a noble. It does not resemble a noble gas. So that's what I want you to do for each of these. Tell me, does it resemble a noble gas or not, based on the charges that I have put. Okay? I'll give you about 3 or 4 minutes to draw out your Lewis structures, then apply these charges to them, and we'll go over the answers in just a bit. 1 or 2 more minutes, we'll go over the answers. All right, let's go over the solutions here. So I'm going to run out of space. Let me do this. We haven't gone over here today yet. Oops, we do not need the periodic table. All right. So, oops, I can't see them now. All right, so let's start with bromine. So first, let's draw the Lewis structure for bromine. So bromine has 7 valence electrons. So my suggestions for what should I do? So you definitely need to know how we get this number. So if you know how we get 7 valence electrons from the periodic table, that's a good first step. Let's see here. Oops, that is capturing that. So if we open the periodic table here, so we know that bromine right here, group 17 has 7 valence electrons. So that's the first step. Then we need to draw all the dots around it. So 1, 2, 3, 4, 5, 6, 7. So there's our 7 valence electrons for bromine. Now I want to make it bromine minus, right? So if I do this, what does a minus mean? Well, electrons are negative, so I'm adding an electron. Does it resemble a noble gas? Noble gases have a full octet, so we would say yes. It resembles an octet. Oh, I just realized the calculator is covering the chat. Hold on. There we go. Sorry. We're not using the calculator today, but it does stick around on my layout. All right, let's do another one here. So we got aluminum. How many valence electrons does aluminum have? Well, if I go over here, we click on aluminum. Boop, there we go. What group is it in? Group 13. What's the ones digit? That's how many valence electrons it has. 3 valence electrons. So, boop, we'll draw that. So 1, 2, 3. And then what we're going to do, I don't know why I skipped nitrogen. We'll get to that in a second. What I'm going to do is I'm going to make it 3+. So if I want to make this 3+, we need to remove 3 valence electrons. So I'm going to go boop, boop, boop. And we're going to erase those. 1, 2, 3. All right. In doing this, did I make an octet? Remember that if I end up on 0, it counts as an octet. So aluminum with a 3+ would be, yes, it follows the octet. I'm going to move this a little closer just so that it... There you go. All right, let's go to the nitrogen one that I skipped for some reason. So nitrogen has 5 valence electrons. I think I fixed my pen issues, thankfully, here. So nitrogen, there's nitrogen. Group 15, 5 valence electrons. So let's draw them. 1, 2, 3, 4, 5. And then what I'm going to do is I'm going to make it N2-, because that's what the problem's asking for, right? So this means add 2 electrons. So I'm going to add 2. 1, 2. I'm going to add, you can add any 2, it doesn't matter. But did I reach an octet? Well, no, I have space right here, don't I? So, no. This does not satisfy the octet rule. And then finally, for P3-, phosphorus is 5 valence electrons. You can see that on the periodic table. I'm not going to bring that back up here. You should have your periodic table open at this point. You can find it. There's my 5. Now what I want to do is, this problem said P3-, so I'm going to make it P3-, which is add 3 electrons. So I'm going to add 3. 1, 2, 3. Did I reach an octet? I did. And there you go. So what this exercise was intending for you to do is to manipulate the number of electrons by adding or removing them. When you have a plus charge, you have to remove electrons. Because remember, electrons are negative. When you have a minus charge, you add in electrons because electrons are negative. And if you get to 8 total electrons after you've done your thing, then you have attained a noble gas configuration. You have filled an octet. Now, why is this important? We care about the octet because the octet is going to be the stable form of the ion that we observe. So there's the homework practice. You can write that down. You can pause the video. Now, the ion that we are going to form is going to follow the octet rule. Now, this slide is just a review. We talked about this in Chapter 3 very briefly, that ions are different numbers of protons and electrons. If you gain electrons, you become an anion. If you lose electrons, you become a cation. Very important to remember, electrons are negative, so gaining electrons means more negative. Losing electrons becomes more positive. That's probably where people get hung up the most, is because, wait, I'm removing something. Why is it positive? Because you're removing a negative thing. Think of it like this. If I have 0 and I remove -3, what do I have? I have +3, right? Because subtracting a negative is like adding. So when you think of it like numbers, if you remove 2 electrons, you remove 2 negative charges. Therefore, your total charge is +2. So if you add electrons, then it becomes negative, because 0 plus -2 would be -2. All right. On the screen here, I have a table of here's sulfur. Every time I add an electron to sulfur, it becomes more negative. So here's minus, -2. So extra electrons are being added. Every time I make it positive, I am removing electrons. Note that this is the total number of electrons. These are not valence electrons on this slide. So total. Because the electrons that are not in the valence layer, that are in the core levels, do exist and contribute to the total number of electrons. In general, we're only going to care about the valence electrons, but for counting the overall charge, this is how you get the total overall charge. It's protons and electrons considered together. All right. So what does that mean that we would write for this circumstance here? So I have sodium. Let's draw the Lewis structure for sodium first. So I've got sodium atom. Sodium is in group 1, so I draw 1 valence electron, and it would look like that. And then I need to lose an electron. So subtract an electron. So I'd go like this, and I would just write that. And it now has a charge of positive because I've removed a negative electron. All right. Now I want you to try it. What would you get for a symbol if you took this atom and you gave it 3 electrons? So draw that symbol out. Draw the Lewis symbol. Add 3 electrons. Put the charge in. And tell me what you should write down. Draw both the Lewis symbol and also just the formula. All right, let's go over the answer here. So we got nitrogen. Nitrogen has 5 valence electrons. There they are. And then I'm going to give it 3 electrons. So 1, 2, 3, 4, 5. That's what I started with. Then we're going to add 3 more electrons, which I'll put in a different color here. We'll do green. I just realized that green might not be great to go with red. I apologize if anyone is red-green colorblind. I'll put the ones that I just added real big. There we go. And because I added 3 electrons, the charge is now 3 minus. Now to clarify the comment that somebody had, can you write it as plus E instead of minus E minus? And the answer is no, because electrons are always negatively charged. The positive thing is the proton. We're not removing protons, though, because they're stuck in the nucleus, so we can't reach them. We're only changing valence electrons. So you have to write it in terms of E minus, because electrons are negative. And then whatever you're trying to do, so either adding or subtracting that. So there would be our Lewis symbol, and then if I were just to write the formula, I would write this. So the formula is N3 minus. That's this right here. All right. I'm going to leave these examples for you to do on your own time because we're kind of out of time for today. Now, you'll notice that for each of these, you could draw the Lewis symbol if it was one of the elements that had valence electrons. But some of the elements I give you don't have valence electrons to them. So copper and platinum are transition metals. They won't follow this pattern. So instead, what I want you to do is just write the symbol and then do this to it. So if I lose 2 electrons, that would be this. So this is what I want you to write for these. So only write the formula. Don't draw the Lewis symbol for anything that is a transition metal, copper or platinum here in this case. So we'll go over the answers to those next time. So that'd be Thursday. Try these between now and then. Like, try them right now because it takes like 2 minutes. And then do as many of these homework problems as you can because Chapter 4 is where we start to tie all the things that we learned in Chapter 3 together. And we're going to need all of this information for later chapters. So it's very essential that we understand how to draw Lewis symbols. All right. But that's it for today. So we'll go back over here. I got to go get my little music thing here. Quiz number 2 is due tonight. That will close tomorrow. The last call email should go out at that time. Quiz number 3 is due on Thursday. Last call for that is Friday. We're going to talk about lab number 2 on Thursday. Just a little bit. Lab number 2 is basically a bunch of videos that you're going to watch and answer some questions about. And it relates to chemical and physical stuff, I believe. Yeah, so that's where we're at. And, oops, I got to hit this so you can hear the outro. So, thanks for coming out to the lecture. Let me know if you have any questions in the class Discord or over email. We'll see you on Thursday. Take care.